16, Higher Level Kinetics, Volume 7, How do we determine the activation energy? In this volume, we look at the Arrhenius equation, we look at plotting it, and we look at using the equation. So the Arrhenius equation basically links the rate constant with the activation energy and this Arrhenius constant. Now, we know that increasing the temperature increases the rate of reaction, there's more collisions, and they have greater energy to overcome the activation energy. And Arrhenius knew this and developed this equation which links a number of those factors. But it also links this constant called the Arrhenius constant. Basically, the equation says that if temperature increases, the rate of reaction increases, and that's the relationship between T and K. So Arrhenius came up with his equation where he was able to determine the reaction rate and the rate constant, but he also came up with this factor that had a fraction of collisions that are occurring and the orientation that these collisions took place in, and he called that the frequency factor. So K is the rate constant, A is the frequency factor, and EA is the activation energy. Now, both of these equations are in the data book, but we use the integrated version, ln K equals negative EA over RT plus ln A to work out the activation energy. So if we graph the Arrhenius equation, we're able to determine the activation energy by using the integrated equation. So we can rewrite this equation as ln K equals negative EA over R times 1 on T plus ln A. Now this gives us a y equals mx plus c setup. So we're going to try and make this a straight line, where y is ln K, the gradient is negative EA over R, the activation energy, and c, the y-intercept, is ln A. So if we graph this particular reaction, we're going to get a straight line. And what we want to do is use the gradient of this straight line to determine the activation energy. R is the ratio, 8.31, which is in joules per mole. So our activation energy will be in joules per mole as well. So here we have a situation where we have a reaction. It's been measured at 5 different temperatures, and we've been given the rate of reaction. So we've got K and we've got T. To plot the Arrhenius graph, we've got to transform K to ln K, the natural log, and T to 1 over T. So simply by going through and doing this, and there's no easy way or quick way to do this, if you're asked to do this in an exam, you have to do this. You have to transform ln from K to ln K and T to 1 on T. They usually give you the graph and you just have to work out the gradient. However, in times I've seen them not give you the graph and give you the data. So here I've gone through and filled in the data for ln K and 1 on T, and then I've used Excel on the next page to plot the graph. We have a line of best fit running through the points of the graph, and what we want to try and do is we want to try and find 2 points that are very close approximations to the line of best fit and use those to determine the gradient. The important thing here is to make sure you get your gradient correct. So the 2 points that I've picked are those two there. And to find the gradient, I'm going to use m equals y2 take away y1 over x2 take away x1. And once we find the gradient, then we can work out the activation energy. So a common thing where students will go wrong here is they'll get the x's and the y's the wrong way around, and they'll end up with the wrong result. So it's a good idea to go through on the graph and write in your x1 and y1, your x2 and y2, and then use the data to get the values for the points. So my x1 is there, and my y1 is there as well. And then I can write my x2 and my y2 from the points on the graph. Then I'm able to put those into the formula for the gradient, and it makes it a lot less likely that I make a mistake. So now I substitute those points into my gradient equation, and that's going to allow me to calculate the value of this gradient. Once I've got the gradient, then there's one more step to working out the activation energy. So the gradient for this graph is negative 22820, which I'm going to write to three significant figures because we've been working in three significant figures. So negative 2.28 times 10 to the 4. Now that's not the activation energy. So we need to use m equals negative EA over R because that's the gradient to work out the activation energy. So the activation energy, I'm going to cancel off the negatives. So the activation energy would be 2.28 times 10 to the 4 times 8.31, the gas constant, which gives me 1.9 times 10 to the 5 joules. Activation energy is measured in kilojoules per mole, so I need to divide that by 1,000 to get it into kilojoules. Remember, activation energy, kilojoules per mole. Here's another past exam question where they gave you the ln(k) and the 1 over t, but again you're asked to do the graph. Some top tips: remember to change EA into kilojoules per mole, and remember that you've got to plot the graph of ln(k) versus 1 on t.